We present the IKEA Ego 3D dataset, a new dataset for understanding furniture assembly from Ego View 3D point cloud sequences. The availability of a large labeled video dataset is a key requirement for applying deep learning methods to solve various computer vision tasks. In particular, 3D data offers many advantages in this context, especially in scenarios where the video is heavily degraded or in safety-critical applications where redundancy is needed. In the context of understanding human activities, existing datasets, while large, are often limited to an RGB camera and provide per-frame or per-clip action annotations. To enable richer analysis and 3D understanding of human activities in the context of furniture assembly, we introduce the IKEA Ego 3D dataset. Each assembly in our dataset contains a sequence of RGB frames from the assembler's Ego view, a depth frame with the required camera parameters to produce a point cloud in a unified coordinate frame, and atomic action for each frame, composed of a verb-noun pair. The dataset consists of 174 assembly videos containing 493,000 point cloud frames, each annotated with one of 56 atomic actions. Each atomic action is composed of a verb and noun pair. Overall, there are 22 nouns that specify the assembly parts, fasteners, and tools, as well as 12 verbs describing a particular assembly motion. To efficiently process the data, we subdivide it into clips containing 32 frames each. For training, we split the data to contain 10,689 clips in the training set and 4,566 clips in the test set. Each video in the dataset contains 2,836.6 frames on average, and the average action duration is 46.2 frames. Due to the nature of the assemblies, there is a high action imbalance since some actions are longer and are repeated multiple times in an assembly, and others are short and occur once. For example, the spin leg action repeats 4 times when assembling a table and takes much longer than laying down a screwdriver. Here, you can see the distributions of number of clips and number of full sequences as a function of action duration measured in frames. Here we show several example frames from the Kallax drawer assembly. It shows the RGB image, point cloud, and action label in the top, middle, and bottom row respectively. Note that the RGB and depth sensors have different receptive fields, yielding points without RGB values. Similarly, here are additional examples from the Beckvam-Stuhl assembly. We evaluate prominent 3D action recognition methods on the raw atomic actions in 2 subsets clustered by nouns and verbs. For 3D action recognition, we compare single-frame baseline methods including PointNet, PointNet++, and set transformers, as well as sequence-based methods like PSTNet, P4 transformer, and 3D in action. The results show that the dataset poses a great challenge for action recognition, in particular compared to 2D video datasets. It also shows that there is significant boost in performance when incorporating a naive temporal smoothing baseline into all per-frame approaches. This strengthens the notion that temporal information is crucial for inferring actions. In another experiment, we cluster the action classes by nouns and report the performance of state-of-the-art approaches. This experiment demonstrates the spatial quality of the method, or how well they capture objects. As expected, all methods benefit from noun clustering. In particular, the per-frame methods have demonstrated a larger boost in performance attributed to their ability to obtain a better global geometric representation since they don't have temporal parameters to optimize. We then separately cluster the action classes by verbs and report the performance. This experiment demonstrates the temporal quality of the methods, or how well they distinguish motions. Verbs are inherently more difficult to recognize than nouns because verbs must accumulate sequence information, whereas nouns can be recognized by a static frame. The results show that all methods benefit from verb clustering in most metrics. Despite the clustering, these results are consistent with the non-clustered benchmark and demonstrate that, as expected, temporal information is beneficial for recognizing the verbs. Finally, to get a better sense of the data, we visualize the point cloud sequences of a clip from the TV bench assembly on the left and the Kallax drawer on the right. These clips highlight some of the challenges of working with point cloud sequences. For example, the head motion causes points to appear and disappear, there is variability in point density, there are different forms of noise including veil points, jitter, and occlusions. All of these challenges strengthen the necessity of this dataset, as learning-based approaches can learn robust representations that overcome them. In summary, the IKEA Ego 3D dataset is an Ego View furniture assembly dataset for 3D action understanding that provides a challenging testbed for computer vision algorithms. The dataset is publicly available for download on the project page. The processing, visualization, training, and evaluation code is available on GitHub. Thank you for watching.